Okay, this is lecture 16, and today we are going to learn more about wetlands. Wetland is not a green infrastructure per se. The reason is um, there are natural wetlands. Nobody designed it. It's part of the ecosystem. But over time, because people start learning that wetland is very useful, people start to develop designs that they can construct wetland at different locations. So then wetland evolves with different design, shape and size. So that's what we are going to learn today. So many of the things that we learn today is not natural wetland, it's a constructed wetland. Um, and in fact, this is the last green infrastructure design class. Next week, we'll learn more about the modeling of stormwater management. So at least we're not going to have entire, how the modeling works, all that. We'll just list models and you should know what those models are, what people use. And I'm also trying to make sure that I have one student who graduated long time ago, not long time, 3 years ago, and he has been working in the industry of stormwater and he does modeling all the time. So I was trying to get him to come here to give a presentation to show that real world what he does. That way you have some idea that how you can do the same thing with different models. So again, it's model means it doesn't mean that you learn the modeling. It's instead how to use that software. That's why I didn't really give that much importance. Because it's more about looking at the instruction manual, like how you learn Excel, how Microsoft Word or any kind of software. This is the same thing. You click different buttons, you export the design, and then you run it. So it's not that trivial the way I said it, but at least it's not about, you are not learning what goes inside the model, like how Excel does the calculation. You don't know the coding. You don't have to understand. So what I'm trying to do here is that you next week you learn the concept behind those models, what each model does inside, so that you know the math or the science behind it, and actually how to use the model. That's something you learn through YouTube's or instruction manual. Okay, so again, office hour anytime by email. So I prefer usually uh, Wednesday, Thursday, and Friday. Okay, so email me to meet any of these days. Tuesday is also okay, as long as it's. Now let me see my calendar. So Tuesday usually AM time okay, because PM we have class as well as we have seminar and other meetings. So Tuesday AM is fine. Monday is pretty busy. So any other time, just send me emails and I'll see that time I'm available. If not, I'll tell you which time in that day I'm available. Again, quiz 4 is next week. That's on Thursday. That's the last quiz. That will be mostly on permeable payments, green roof, and wetland. So that means this week of class um, and the one class before exam, permeable payments. So those are the 3 lecture slides that you need to read. Homework 5 is mostly about um, work quantity modeling, right? So that's why I said that this is one homework that you will do in the class. You know how to do it. It's just we didn't really solve many examples. So we'll have just one question that's on Excel. I'll solve it here. You just repeat the same thing in at home for a different type of rainfall. So this is just a submission is 100% credit. I just want you to know how to do this one. This is on, by the way, unit hydrograph. And complete project draft is due on end of week 9. The reason is we want to give you the comments on week 10, and then you can submit anytime after the final class or the after the last class. So we want to make sure that you have the comments by the last class when you are presenting. The final weeks mostly will be presenting, learning different project. So that's not any lecture slides. So again, keep writing and let Renan knows when you finish something so that he can give you specific incremental comments for different sections. But once you submit project draft, I'll read the whole thing. That's not Renan, that's me reading and giving you comment. Okay. So that's pretty important because project draft, if it is I don't take any points off for whatever project draft you have. But if you have a really poor project draft, I'll give you so much comments that you have to work a lot in the last week, which is the time you are final. So that's why I really prefer you guys to work these 2 weeks, so that when you submit a project draft, it's kind of you did your best, and then I'll give you some very basic comments, and you can address them the same day or next day, and you submit. That way, you are done with your this class. So make sure that you work a lot more now than after I getting my comments, because that's just easier. um, Today we are going to learn about wetlands and how they work. Um, and one thing, every time I talk about wetlands, I remember in one of the conferences, somebody was presenting wetland as a keynote speaker, and then he basically do a rap on wetland right there on the stage. And the same person, actually not same person, somebody else did the similar rap on wetland. So I always play that music. So I'm going to see if we can play that YouTube video. So let me see if I can. So let me share the screen. New share. Let's see. This is Google Chrome. Okay. So basically, search wetland. Now you see the screen. So let's search wetland rap. Okay, that's the one. The very first one that you see is the wetland rap. So let's see if I can share the music. Hold on, stop share. Share the sound. Okay, that's a good one. Okay, so let's see.
What a gas, better look fast. I bet you never heard a rap from a blade of grass. Yeah, I'm a Reed, Reed is my name. You gonna be digging me next time we get a lot of rain. Me and my cousin, we soak up a whole lot of water, keeping things balanced like a living on a teeter-totter. Our roots go down into spongy mud like a game of Red Rover. We're holding back a mighty flood. Come on out and visit, canoe through. You gonna see us standing tall, waving at you. Oh yeah. Alright, here we go. We're living in a wetland, a wetland, a wetland. Right there where the water meets the dry, dry land. We're living in a wetland, a wetland, a wetland. Talking about all the herons, alligators, and clams. Hold it, man. I am a clam. My name is Sam the clam I am. I slurp the water in through my snorkel-like snout. Then I filter out the floaties and I spit the water out. I'm eating plankton, those little plants and critters are floating in the water, teeny tiny like glitter. Poisons in the water hurt the humans and the otters, so I have a heart and do my part just like I know I oughta. I store pollution down in my insides, feeding up the water through the low and the high tide. Low tide, high tide, low tide, here we go. We're living in a wetland, a wetland, a wetland. Right there where the water meets the dry, dry land. We're living in a wetland, a wetland, a wetland. Talking about all the herons, alligators, and clams. Well, excuse me a minute, cause I'm gonna get bossy. My name is Maurice, captain of the river posse, 20 foot long, king of the alligators. I spend my days a hooping up on contaminators. Me and my posse, we can take all of the toxins. Gasoline, sewage, phosphate, dioxin. Join our posse, be an ambassador. We don't wanna go extinct like the dinosaurs, cause there are fish, amphibians, and reptiles, bugs and birds by the billions gonna chill a while. Water snakes, lake on the hunt for a bullfrog. Whooping crane, whooping it up in the morning fog. Willow is a snack for the beavers with the flat tails. Muskrat likes to hang by the cattails. This is a habitat for so many species. It's like a puzzle, but pictures are complete. Unless you save all of the pieces. Sing it like we're underwater. Here we go.
All right, so that's the wetland song, and I really like that initially, but I heard it so many times that at some now I don't enjoy as much I used to before. Um, let's see some chat window. Yes, I guess if any of you are in musician or write songs, you can write songs for things that you do. Um, I'll be probably as awesome. I'm pretty bad at songs. So I'm not very good at music either. All right, so this is wetland. So what you learn is that that pictures that you see is basically land full of water, right? So it's a shallow water lands, are completely wet. That's why it's called wetland. But what you are going to design for stormwater is not look like that because it's not. I mean, you don't have that much space in any cities, so you can't really build a wetland or design a wetland unless you that space is natural wetland. So what people do is they create a small scale wetland in the big cities, and they define it different ways. So sometimes the wetland you not even see water on the surface. That's what called subsurface wetland. It functions very similar to rain garden. So we'll learn about all that. Okay. So how it's going to work in the wetland, you can check this particular videos that will tell you. But if you see wetland, this is how it looks. So the nearest one you can visit is Bahana Creek wetland. So I put some of the pictures that you can access in Southern California. So particularly Chino Creek wetland is something one is very beautiful. You might visit there. So there are many ecosystem benefit of wetland. In fact, wetland is the nature's first wastewater treatment plants. Okay, so that's where most of the pollutants are removed naturally. So learning how it works in the wetland, people design the wastewater treatment plants. For instance, people learn that if it is shallow waters with lots of sunlight, you can kill pathogens. That's basically inactivations. Because it's shallow, it's very easy to aerate it, or the oxygen concentration is high. So that's the reason aerobic degradation is much faster there. So that's why you see that the shallow rivers or the contact bed reactors, this operate similar as wetland. But then there are some pollutants you can remove in presence of oxygen. So in that condition, you need something anaerobic reactors. And in wetland, the very bottom portion of wetland, near the bottom of the water tables, not water table, the below the water, you see that top small layer of biofilm is called biomat. That basically serves the function of degrading a lot of pollutants. So as long as the pollutant get into that biomat, microorganism will degrade it. So these are different function you learn, and I just want to say that this is very natural process. And our goal is to maximize that process, how to increase that reaction kinetic so that you remove a lot more pollutants from stormwater. And typically wetland is used for recreational purpose, so we are obviously stormwater treatment systems are not necessarily always recreational, because people think that they have pollutants, that's why people don't get in. So but some places you'll have something like canoeing or just people walking side by, they're not using that water for any reasons. So this picture shows that you can construct wetland in places by just digging soil so that you can create a pond or shallow pond. So this picture shows that how you can start it. And let me start with water comes from the one side and leave another side. And the very first is to remove sediments, suspended sediments or the large particles. Because if you don't remove the large particle initially, it will it will it will bury the wetland. So all the things that you dig is going to be all completely buried at some point because of sediment depositions. So why that's why initially there is a retained sedimentation pond which is very deep, and the idea here is that you all the particles settle, large particles settles there, so that that way as the sedimentation pond becomes shallower, you can uh, dig again and remove that sediments. That way you can protect the rest of the wetland. So that's why you see sedimentation pond is always initial part of the design. So you see that over here, sedimentation pond. That's how it look if you look from the top view as a bird eye. And then as you can see, the stormwater is channeled underground with a pipe here. So that pipe to a next pond. Okay, so that pond is inlet pond. Then in the rest of the places, the entire thing is called this is entire thing is wetland. But as you see, the pond depths vary. At the center, there are lots of plants, and with time, the gradients is increasing. So at the center portion, you have more vegetation, and there is a reason for it. Because if you have more vegetation, they remove certain type of pollutants, and they remove nutrients if it moves slowly. But other places you need to have open surface because that's where you can remove pathogens by sunlight. So you don't want to cover entire surface with sunlight because then you don't remove certain other pollutants, or you don't want to also have too much plants all over place because sunlight is part of inactivation process or degradation process. So that's why you see the both end you have open wetland where there is no or there is no plants to interfere with the sunlight. The other middle portion you have more plants to do biodegradations. And then towards the outlet, you just discharge it. So there is no other aspect of it. So as you see, the functions that you are going to use is sedimentations, contaminant removal by degradations, and also by plants. And then you can also change the only thing you can control here is the depth of the surface and how quickly the water is going to flow, because it relies on slow moving water. If it is moving too fast, the reaction is not that efficient, so that means you will not remove a lot of pollutants. So that's why a lot of times you see wetland, they are very tortuous. Means it's moved in a very, it's like a snake. That way it has longer time path for the for the water to exit the systems. There are some limitations, some concern about safety related to public access, because a wetland all the time moisture, it's a breeding ground for mosquitoes. So that's another concern. The third one is you cannot use wetland unless it's a flat surface because it's require water to move slowly for this to remove pollutant. So that means if you are in a location which is very like slope is high, you can't use this as a green infrastructures. Then also you need to have base flow, supplemental water, because the wetland works if you have enough water, particularly above ground wetland. So a lot of times, like in California, or particularly Southern California, most of the wetlands are fed by not just stormwater. There has to be some other form of water, like stormwater or gray water or recycled water. Particularly in this case, recycled water. So many of the wetland you see in Los Angeles are actually discharged from some wastewater treatment plants. And also the biggest challenge here in Los Angeles is doesn't have enough space. So if you want to design new wetland, you have to find a space that is not used for anything else. That's why in many places like in Burbank, there was a old landfill slide, not landfill. That's the place where car and other it's a dump yard for the cars. So they remove that one and they're trying to create a wetland there so that public can use it. Because right now it's not too polluted, but it's just basically nobody is using it. Constructed wetland for stormwater treatment systems is again you can design it by once you know that where is the space and how much water you can receive, you can design it. This is one example. Predo or constructed wetland there in near Santa Ana rivers in Orange County. If you get a chance, you can visit there. All right, so let's see the component of wetland. As I said, it's very simple. It's basically detention pond, an extended version of detention pond. The difference is detention pond, you have more depth. It doesn't do any other functions. In wetland, it's critical to have shallow depth. That way that biomat is going to interact with water. And you may have detention pond as a pre-treatment strategy. So this is we discussed that this is the idea is number one is sediments, sediment trap. So this one you can use by a pond, and you already know how was the design. So you basically control the flow rate and volume or area. And usually you don't need to have any plants there. Sometimes you have also plants. Plants also serve as a function to trap some sediments because it retards the velocity. And the second one is mostly um, so this is basically pond is the first part, and then the second is plants or vegetations. And these kind of vegetation should survive in wet climate because these are going to be wetland. That means you will have all the time water. But so that you need diverse type of plants that can survive. So that's the second component. Mm, Third one, which we don't see it here in the design, is the biomat. So let's say this is soil and this is water. Water is flowing here. So the this location you have sediments. So this is biomat. Okay. So that thickness, first 2 millimeters or let's say quarter of an inch or less layer is the one that degrade a lot of pollutants because that's where the exchange of if you see how they look. So basically, this is basically you have pollutant here in water pollutants, and this is sediment. Okay. So then your contaminants will move these directions or other directions based on that exchange rate. So for that reaction to be efficient, you got to have slow flow rate of water. So most of the wetlands are designed such a way that water moves very slowly. Okay. And that's one of the reason you need a large space because moving slowly, that means you large footprint for the retention time equivalent to 48 hours. So many of the wetlands, the retention time means once it enter, the same water for it is to exit, it will take 24 to 48 hours. That means the size has to be much bigger. So these are the things you can. And the fourth one is basically depth. The reason why depth is important is because of sunlight. So if you have sunlight, the light can kill pathogens. But as it goes deeper and deeper, the sunlight intensity will decrease, the UV light will absorb on the top surface. So you will not see enough UV light for inactivations. So this is for solar inactivations. So that means, if you need to remove pathogens because of sunlight, you got to clean that area for any weed vegetations or not. So these are the main component of wetland. Um, and the things that you can control is the depth, size, and the flow rate. Um, all right. So as I said, these are the different design, and people start thinking of how we can create wetland in a different place where it doesn't require large, large space. So that's why now people start thinking of surface versus subsurface wetland. The difference is whether water is moving above the grounds or below the grounds. So in the subsurface, it's like biofilters, but it's moving horizontally in one end to another. So that's why it is it doesn't require that much space because your contaminant removal is not dependent on that interaction at the sediments. What it does, it goes through the entire soil, so that means it filter more of the pollutants. Subsurface wetland could be vertical versus horizontals. Means water moves from the top to bottom or side to side. But vertical flow wetland is similar to rain gardens, because if you think of rain garden, it moves from the top to bottoms, or biofilters. These are all operate in the same way. Okay, so these are similar. Vertical wetland is similar to all those two. Horizontal flow is basically it's moving one side to another. Um, I give you a handouts or I'll upload it so that you can read it, but basically that's the differences. So this is just for discussion. I didn't share, but let's discuss it now. Which one you think won't be able to remove effectively? Um, so again, I you don't know this answer because I didn't tell you, but this is the reason we want to brainstorm it. So let's say what you can think of. Which of the contaminants is difficult to remove? So think of the process that needed to remove those contaminants, the main process, and then you think of whether wetland is designed such a way that that can remove. So I'm going to write the process here. Sedimentations, the typical remove. This is adsorption. This is some or plant uptake. This is solar inactivations. Okay, so based on that, which one you think would be, you can design effectively. So think of both subsurface wetland or surface wetland. It doesn't have to be one type. Okay, I'll give you 10 more seconds to answer for those who didn't answer yet. Okay, well, I'm going to close in 5 seconds. All right, so share the results. As you see, this is pretty mixed. In fact, the right answer is one of the one which is chosen less between A and C. So let me stop sharing and relaunch again. So If you have to choose between A and C, which one you'll choose? So the answer is which contaminants is difficult to remove in wetland. Not easy to remove, or you can design it effectively. In wetland, you have a sedimentation tank, right? So that means you are designing specific for that purpose. So that means A is not the answers. So the real answer is actually C. So let me tell you why. Let's go back to the um, let's go back to the graph here. If you see sediments are removed in the, it's called sedimentation pond. That means it's designed to remove sediments, right? So that is removed here. Adsorption is basically can occur if metals can stick with any materials. So the wetland is shallow. That's why the metals can bind with that sediments most of the time. So at least it has some surface. And adsorption is doesn't take that long. So that means it doesn't require that much longer time for adsorption to occur. Usually adsorption is pretty instantaneous or effective if once as soon as it find the adsorbent or the materials. Pathogens to remove, it's all you need is open surface so that sunlight can inactivate it. As long as you have open surface, you can do it. For nutrients, you need plants and a microorganism. And because a biological process, it's a very slow process. So that means in most of the places, even you have plants, doesn't mean that they can take as much nutrients as they can needed to from water. So that's why it's very difficult because a biological process. It's a very slow process, and usually you don't have enough time for the. By the time the removal can occur, the wetland water has already exited the systems. So that's why number C is the answer. Just because it's a it's a slow process and um, wetland doesn't um, retain water for long enough to remove nutrients. If it is adsorption, you could have removed it. It's not adsorption. That way, in adsorption, you can use subsurface wetland so that you can everything move through a soil, and the soil has adsorbent to remove heavy metals. So then you can remove it just by adding compost or organic mulch, or just have organic material in subsurface wetland. You can remove most of the heavy metals because it's sticking with. It's like a filter media. For nutrients, it's not about adsorption. It's more um, degradations. So the removal process is these are the removal process you can think of. Sedimentation is one of the process where you can remove by because of the pollutants in the large particulates that could settles. For the filtration or chemical precipitation, that's where you need when there is a, let me put this way, let's write it so that you can see. So let's see, sedimentations basically this one. So the velocity, the way you can design is settling velocity. You know this one from the other classes. Particle density minus the water density times acceleration due to gravity and particle size. So particle size square divided by 18 and viscosity, which is mu. So that's the velocity of settling velocity, and particles removal is basically settling velocity divided by overflow rate. Okay, if your settling velocity equal to overflow rate, then everything is removed. The settling velocity is is or the if the overflow rate is faster than settling velocity, um, that means that before it settles, some of the particles will overflow. So that's how you can calculate that. Um, then next is filtrations. Filtrations is basically, if you have plants, it can remove a lot of trash. So that's why you can see that many microplastic, not microplastic, large plastic can be filtered by the plants. So this one is, let's say, trash filtered by plants. And then for chemical precipitations, and another thing I want to say is filtration can also occur through the soil if it is a subsurface wetland. So this is also um, subsurface wetland. The soil itself is a filter media. Okay, soil is filter. Chemical precipitations is very unlikely because that's where, if you have pH changes or you have a lot of salt, then thing can precipitate. Adsorption occurs at the biomat. They said that the sediments interface, sediment water interface, and but it in subsurface wetland, it can absorb to the soil too. Okay. And uptake and transformation, this is basically on plant, and this is for the microorganism is in biomat. Okay. So that means if you want to extend the removal, that means you have to put more plants, or you have to make sure the biomats are pretty thick. Predation or die-off is only for pathogens. Okay, if you have pathogens, they can die because there are other microorganisms who will compete for the nutrients, and so that is because of that. But most of the time for pathogens, it's because of sunlight. Then it says UV light from sun that will kill the pathogens. Okay, so these are different mechanisms that you could think of. And in different papers, people try to model all these mechanisms, and you already know this mechanism from previous slides, so I just reiterate here. um, so if I ask you a quiz questions where I ask, which contaminants, which how contaminants get removed, sediments, what is the mechanism, you write sedimentations or settling. For heavy metals, it's really adsorption to soil, biomat. Okay, there is some plant uptake, but this is low efficiency. So this is the reason mostly that occurs. For nutrients, as I said, this is, it could be plant uptake, but plants takes very small amount. They don't need that much, and or biodegradations environment. For pathogens, there are multiple, like sunlight is one thing. Sunlight inactivations. Pathogens can also adsorb on soil if this is a adsorption, if it is on soil. So these are the process you can think of. For the sedimentation, as I said, you know Stokes law, but in the handouts I gave you, this is the equations that you can use to calculate it. And basically it has a couple of factors. So the first is the flow divided by area. That will describe, how quickly things are moving per unit area. And Bs is the settling velocity. This is settling velocity. And these are basically, these are the different depth and other depth at different locations. So that's the, if you use this value, you will be able to calculate how quickly it can be removed. And that's difference from Stokes law. The reason is account for different factors like depth and other aspect. So that means you can use this one for mostly for the design. Um, for the quiz, sometimes you'll be asked, what affects contaminants removal. So, for instance, sunlight is affected by the depth, and biofilm would be affected by the biomat and plant. The reason is the plant itself decompose, that will give the nutrients to the biofilm. So that's how biofilm become healthy. But if you have no plants, there will be very little biofilms. And the plant, the control is density, depth of root. Um, so these are the process you can think of. Hydraulic retention time is something, it depends on how much water that you can treat. You have area, let's say that's your area, and the depth is let's say d. So that means volume is area times depth. If you see this is rectangular, and your flow is q, you know the hydraulic retention time, or HRT, is um, volume over q, and you need HRT as small as possible. Okay, so smaller is better, so that's more time for pollutants. But this is something you cannot control. You cannot control volume because you don't have much space. So the only thing you can control is flow rate. And so that means you have to store water, stormwater somewhere, and release slowly. So if you are using wetland, and this is the design configuration you can have. So for wetland, this is the equation you can use to decide how much volume it can store. That's basically, again, it quantify based on area times the height, and that height is a function of a lot of other factors. So that's why, this is just to, so if you have to calculate how much, what's the size of the volume of the wetland, you can use these known volumes like this. Again, this is just for your projects. You are not required to understand that factors. Okay, so let's see how much we learn. I'm going to generic poll.
I have a quick question on
Yeah.
that. On the last slide, where you're showing hydraulic retention time, were you saying that we wanted that value to be very small or large?
Okay. It should spend long enough time. So that means the retention time has to be large. You're right.
Okay.
Yeah,
Thank you.
I was thinking correct, but then right, totally opposite. So longer retention is better because more time for contaminants to get removed. Okay, so which of the following modification would improve denitrifications? So again, think of denitrification as biological process. Biological process is slow. That means you have to use high flow rate. I guess there is some noise behind. All right, so a few more seconds before we close this quiz. Which of the following modification would improve the denitrifications? The key here is that it's a slow process. So that means if you give long enough time, that will improve. So which one will be the answers? That will give you more. And then also it's a biological process. These are the two things you have to remember. So wherever it gives you more, um, okay, I'm going to end the poll. So let's say high flow rate. High flow rate is obviously it's going to decrease the time. So that means this is not the right answer. Um, a large tree. Large tree doesn't have that much nutrients uptake because the roots are pretty deep, so you don't really see from the water. So that's not going to work. So now you leave with a B or C. Deeper biomat layer means you have more microorganism. If you have more microorganism, it's more likely that will also remove more nitrate, partly because it's or nutrients because it's a biological process. So this could be one cell. Shallow flow. Shallow flow means if you have let's say this versus this. So in this case, you have most of the, let's say you have nitrate here, nitrate phosphorus, and your microorganism is here. This is the sink. So in this case, left side, most of the water or most percentage of water is in contact with biomat here. So that means more contact volume or contact area. So contact area per volume of storm water is high. So this is shallow, this is deep. So that means shallow can also help. Okay. So one of those two answer could be fine. But if you write deeper biomat layer, that's the first choice because it has more microorganism. Okay, so now that you learn, let's see how people design it. So the design process is pretty simple. What you do is you first decide why you are designing. Why? That means which pollutants to be removed. Usually every pollutants can be removed some extent, but if based on that you can change the size of the scope of the wetland. For instance, if your goal is to remove nutrients, you know that you don't really care about the ponds because you need more plants. So then you can add more vegetations. If your goal is to remove pathogens, you know that you don't care about vegetations. You're just going to put more open space. So that design objective is important. Okay, so based on that, um, these other things are designed. So again, I'll upload the handout so that you can read it. Again, this is for you who has wetland um, as your project design. So a couple of things you have to think of is wetland is not like a active system. That means you want water to move naturally. That means it has to be in the flat surface. It has to be also slow flow rate. That means you have to control that gravity flow. You have to also design based on the climate, because if you, for instance, if it's biological removal, the removal will be very slow in winter conditions. So that means if it is a winter place like in Canada, wetland doesn't work in winter because almost all frozen. So you got to think of that if you are designing stormwater, what season you have to account for. Another thing is you don't want to destroy the landscape when you design it. You want to have the most natural flow. Otherwise, the water will find its own way, erode the land. So that's why never create a wetland where you have to change the flow directions. Just let it go with the nature and use the landscape as its own as a part of the design. And wetland again, just think of this as a natural system. So you rather want to have it as natural as possible. Don't have to over engineer it. Don't put too much different structure. Just have simple flow rate and in some shallow pond. So and again, wetland is not designed over any sensitive area where groundwater pollution is a concern. If it is the case, then you have to entire place you have to put a liner below it, which is not feasible if the space is too high. So all these things you have to consider. So again, these are all written here. I'm not going to look at it, but you can read it for your handouts. Um, so this is what, as I said, I discussed that. I'm just going to list it one by one. First, for site selection, you have to think of what's the source of water and the slope of the locations, whether there is a groundwater nearby that will be polluted or not. So historically, you should not use it any floodplain because it will all flooded and it will destroy the wetland. And you should not also put in a place which is protected area. And so for urban stormwater, this is source of water is basically waste water treatment plants. Okay, so anywhere there is a wastewater treatment plant, this is a great way to start this one because you have the effluent discharge. You just design wetland to discharge the um, recycled water. Then second thing you want to do is the how the whether you will have a liners or not. That based on the whether you want to protect groundwater or not. This is equal to protect groundwater. Inlets is basically based on the flow velocity reductions. Because if you have a wetland, you don't want it to be destroyed, the plants to be uprooted if the flow is too high. So the inlet design, whether inside or how below it is, or whether there will be some rock in front of it, all that stuffs can be designed like here. So this picture shows that how it is designed. So sometimes you can put inlet as a pipe, perforated pipe. That's where it releases the water, or it could be just one location as a pipe. Then you put other stuff to slow the flow, or it could be below or above the level of the water. Vegetations, usually you rather have the vegetation which is native to that locations. So look for those vegetations, and this is just a list of vegetation written here, and it's how much water you can tolerate. Okay. Maintenance, again, the one thing that you always have to look for is the plants. These are the bio indicators. If the plants are dying or plants are not surviving, then your wetland is not functioning well. Hydraulic retention time is something you check every few years, because usually if the sediments are deposited, water will divert into different sites. So that's one thing you have to check. Ashes is not really a problem. You just have to make sure that you can reach out to every other places. So that's wetland. So again, I'm going to upload the handout so that you can see it. When we come back, we'll take a 10 minutes break. When we come back, I'll give you some tips about preparing your presentations, which will be next week. Next week class, almost not next week, week 10. So that means next week you'll be preparing your presentation slides. So what we'll do is we'll go through some few tips, but we'll also watch some other presentation from last year. I also gave you link here, and the reason is you can watch them on your own time. You can also see different projects they did in last class, so that you can see which presentations make sense and which one, you can feel it, which one is a good presentation versus other. But they are all they all share the slides, and I give them feedback. And so what you see is the final version. It's not the how they started, but so that means it will give you some idea how to do these presentations. Okay, so I'm going to stop sharing now, or I'll stop recording or pause recording. So you have presentations on the final week of the week 10. Every group are going to present. Um, at least, in the reason before people can record it and send it to me. But because we have time, and also you learn a lot more from each other projects when somebody else presents. So last two classes all presentations. So you just have to tell me whether you are presenting on Tuesday or you are presenting on Thursday of that week. So start booking certain time. We'll have let's say 8 presentations, 8 or 10 presentation based on the group. Maximum, I think 10. We'll have 5 presentations on Tuesday and 5 presentation on Thursday. So you will not, again, you will have only 10 to 12 minutes to present. I forgot the exact time I wrote on the syllabus, but definitely not more than 10, 12 minutes. Um, the goal is to not to explain everything that you have done, because it's not about, you may have done so much, but you are telling a story. So you will just tell the effective story in a very few things that you think most important. You will just present that. Um, so don't try to replicate the entire projects as your presentations, because then you will, because in 10 minutes you can't really explain everything because you might have done so much more than that. So that's the whole reason I want to give you some tips. Um, the very first thing I see is whether you have a story or not. You should have a story because that's what you wrote in your report. But whether you are presenting a story in a compelling way or not, whether students can understand or the other colleagues can understand why your project is very important for that sites or locations, or why it is important to do that. Because remember, this is a sales speech. You are going to present your ideas to a client who is going to pay you to do the projects that you propose. So that's, think of that as your presentations. It has to have hooks for audience to connect very early. You can't just make it too academic in the very early that no, this is a, I'm doing wetland. You got to make it more interesting at the beginning, and the slides should be connected between slides, so it can be abrupt. For instance, you are presenting a story in one slide, next one has to be somewhere related to that. Or if you're too abrupt, you have to give connections. So that means you have to look at the transition of the slides, whether that makes sense or not. If not, then you have to add another slides to connect between those, or at least to connect the stories in a way. The one thing I definitely don't like is the slides with lots of text, or outside text. Um, the best slides are basically one message and one pictures. If you need like 10 pictures in a slides, it has to show a reason, a connections. Otherwise, make 10 slides to show those 10 pictures and present each one for a few seconds, as opposed to putting all them together in one slide. So try to try to see what message you are sending from that slide. Each slide should send one message. Okay, and usually people write, that's the effective way to do is title is the main message. Everything else is just the text and thus the pictures, because you are speaking, so you really don't need that many text. Again, think of this. This is a presentation. This is a storytelling, not about putting all the information so that somebody else can read later. Nobody's going to check your slides after these presentations. So you have just 1 second to get their attention. If you write too much text, nobody will listen to you, and nobody's going to also, they'll lose interest. So these are the links I gave you. So there are 7 projects last year. So I wrote the title, what it does. Project 1 evaluates the design of interpretation system by literature review and apply the knowledge in the conceptual design of a biointerpretation systems at a hypothetical site in San Fernando groundwater basin. So basically, they did a literature review, combination of literature review, and then they did the design for a hypothetical site. So that means that's not real site. They create a problems and they say, okay, if this is a problem, how they are going to solve it. The second one evaluates the most suitable restoration method in terms of ecological and economical standpoints to restore Bayana Creek wetland. So what they do is they look at the existing system, what the Bayana Creek is designed, and they say, okay, what modification they can do to bring more, um, to recover some of the functions or to make it more economy. In the sense, the economy in the sense they want to raise some money for it, right? So that's why they talk about that. The third one, assess the effectiveness of Eco Park Lake So basically, there's a park near Los Angeles. This is the lake that fed by recycled water. So they are thinking of how they can, not recycle water from LA River, and they thought about how we can design this lake better way. And the fourth one is more like a school project. So I know that one of you, the group, is working on a school project, examines the existing best management practice at Sherwood High School and provides alternative design to improve their ability to collect and filter runoff and integrate students' learning. So this is very similar to what one of the group are doing. So you can learn from this particular project. Project 5 optimize characteristic of green roof. So this is more on a green roof to maximize energy saving. Because as you know that um, in a southern California climate, you're not using it for stormwater. It's mostly for the energy saving. So they looked at those aspect of it and then say what features they can have for a building. For instance, for this one they designed on the Bolter Hall. Project 6 explore the design of permeable payments and evaluates many social benefit for their implementations. So that's most on how it works, and they talk about other aspect of it. The last project, they talk about also permeable payments, but in a different climate, in tropical climate. The reason is in tropical climate it rains a lot. That means it also erode a lot of land, so it may have suspended solid that will clog the permeable pavement. So that means what design you could do to decrease that clogging in that particular climate. So they talk about climate aspect of it a little bit more. So these are the different. Again, you can watch any of them. You upload the slides on Campusware. That's what's one of them. So let's watch this one and see whether uh, see I'm going to check the link in YouTube and then I open it up. Then we can watch how they just for a few seconds, that way you can see how it works or how they present it. Um, Hello, this is okay. So let me just stop sharing and start sharing in a new window. So share sounds.
Team Matt and our project for CNEE C159 is integrating student learning and improved green infrastructure at Sherwood High School. So a little bit of background information on Sherwood High School. Like many built environments, it has impervious surfaces which impede natural retention and infiltration of runoff and lead to flooding, erosion, and water contamination. By introducing green infrastructure, we can reintroduce vegetation to the urban environment, reduce runoff, and bring educational and societal benefits for the local community. So a little bit of regional context on Sherwood High School. It's located in Sherwood, Oregon, which is a small residential community about 15 miles southwest of Portland and only has a population of about 20,000 people. Sherwood receives around 42 inches of rainfall annually, with a peak rainfall season in winter and a dry season in summer, and the city sources most of its water from the nearby Willamette River. So this high school that we're focusing on is actually a new Sherwood High School, which is currently under construction to replace an old Sherwood High School. So the students from the old Sherwood High School will be going to this new one, which would be around 1,700 students. The majority of these students come from middle class or affluent families, as only 15% of these students qualify for reduced or free lunch. On the site, the main soil is silt loam, which is composed mainly of silt and clay, but contains around 20 to 30% of sand as well. And so this soil is moderate to poorly drained and has slow permeability. And the vegetation at the completed site, according to the construction plans, will consist of approximately 40 acres of various lawns, around 1,300 trees, 5,000 shrubs, and 555,000 herbaceous plants.
Next, we get into runoff characteristics. In this slide, we calculated the peak flow runoff using the rational method. In order to do so, we firstly determine the runoff coefficient. According to the United States Green Building Council, hardscape ranges from 0.7 to 0.95, while softscape ranges from 0.05 to 0.35. We then followed a common general rule and set our impervious surfaces to be a coefficient of 0.9 and pervious surfaces a coefficient of 0.3. In order to figure out the rainfall intensity, we had to look back at the information from our previous rainfall data. As a result, we noticed that rain peaks in Oregon during the winter, based on the average of the winter months. For accounting for capturing larger storms, we get an intensity of 6.6 inches per month. When converted to inches per hour, the value comes to about 0.00904. Peak flow is lastly determined by multiplying the runoff coefficient by rainfall intensity by the square footage of the area. Q equals C times I times A, and all our calculated values are displayed on this table. Another set of calculations we performed were the runoff volume calculations for each drainage area. This is determined through the curve number method. Some input factors that we made were categorizing our hydrologic soil group to group C because the area seems to have moderate or poor draining soil, setting our standard moisture conditions to 2, and accounting for a 25-year, 24-hour duration design storm to comply with the City of Sherwood Stormwater Management Plan. On the right is a table displaying all these values. Later, we then look at some observations from the topography layout of our project. Noticing by the detailing of the contour lines, the site we are dealing with is pretty hilly. It also seems to be that elevation is flowing down the direction of the map as seen with the red arrows. The flow is towards 2 low points of the site, which is actually where the existing extended dry basins are located for capturing stormwater. Some physical contaminants that may be present in our job site includes sediments as a result of heavy construction and temperature change due to heat transfer from the roofs or asphalt concrete to the stormwater after exposure from the sun. Some inorganic contaminants include fertilizers if the school decides to implement lawns for the sporting grounds, and heavy metals after contact with the buildings and bleachers. There are no organic pollutants, but wastewater may be considered treated if necessary. And now we get to the existing stormwater plan. Here is the existing plan to manage stormwater at the high school. It consists of extended dry basins at the northeast corner of the site to capture minimum water quality volume and detain the water for the 48-hour drawdown time, as defined by the Clean Water Services Guidelines. For Sherwood High School, we calculated that the water quality volume captured by the extended dry basins is approximately 52,850 feet cubed. These calculations are located in the appendix. Although it reduces stormwater runoff, the current plan does not take advantage of educational purposes or rainwater reuse.
So next, we're going to discuss the modified stormwater plan to improve upon the plan that's already there. This consists of 2 different parts, using the roof to capture rainwater for reuse, and creating rain gardens to both reduce the amount of runoff and incorporate green infrastructure. Sherwood High School has a lot of roof space, nearly 180,000 square feet. Instead of letting rainwater either pour off the roof to join ground runoff or get trapped on the roof and evaporate, we suggest installing two large cylindrical basins to store the rainwater coming directly from the roof. Both are located at strategically lower locations of the roof's design to utilize gravity to help the water flow in their direction. Sherwood receives many inches of rain per year, which when multiplied by the area of the roof, results in a lot of roof runoff. Even if the collection basins don't capture every inch of rainwater falling on the roof in total, they still have the potential to collect thousands of gallons of water. To the left, you can see the rough design for the rainwater harvesting system. Gentle inclines will be installed on the roofs to encourage the water to slope towards the basins. Gutters will be in place to both control the flow of water and prevent larger debris such as leaves from getting in the basins. The water then travels straight from the roof to the basin via pipe. The potential amount of rainwater to be collected from the roof exceeds the capabilities of the school alone to use, but a possible solution would be to sell or donate the water to other local companies who may benefit from an easy supply of rainwater.
The second part of the modified stormwater plan is the rain garden situated throughout the school. As you can see in this figure, we can split the school into 5 main drainage areas and place rain gardens to capture part of the runoff from each drainage area. For example, for drainage area 3, water from the parking lot will drain into the vegetated swale in the bus turnaround before being carried by subgrade pipes to the rain garden, where the water will be captured and stored. The rain gardens are designed to capture a total of approximately 262,000 cubic feet of stormwater runoff. We plan to further improve the school landscape with these rain gardens by planting native species such as Douglas aster, Baltic rush, and Highland cranberry. The modified stormwater plan thus presents many benefits. First, it captures significantly more runoff than the existing plan. As this table shows, the modified plan captures approximately 5 times more total runoff from the site. This means less overland flow, lower risk of flooding during long periods of rain, and more treated stormwater. Secondly, our modified stormwater plan presents many educational and communal benefits. Not only will students see how green infrastructure works on their campus, teachers can also introduce concepts in hydrology, stormwater runoff, water treatment, and local ecosystems in the classroom. Additionally, students can volunteer to help harvest plants, remove weeds, or maintain the rain gardens and rainwater capture system. The water captured from the rainwater harvesting system can also benefit the greater community through reuse at local businesses. Thus, the school can strengthen ties with the community. Finally, the green spaces themselves, as many studies have indicated, will also improve mental health throughout the community.
Our conclusions from the research we have done are several. We first want to acknowledge that Sherwood High School does have a good current green infrastructure plan in place, but it can be modified to be even better. These modifications include adding roof rainwater capture systems and bio-infiltration basins, as well as allowing more opportunities to learn about and gain experience with green infrastructure for the students. Green infrastructure is needed now more than ever in a world that is becoming increasingly urbanized. Projects like this are essential in educating, inspiring, and improving not only our society, but the entire globe. Thank you so much for your time.
All right, so I guess that's the presentations that I want to give example. As you see towards the end, the slides are a little different from the beginning. In the beginning, there are a lot of text. Because you are presenting to a computer, not presenting right standing somewhere so that you have to memorize, or if you want to memorize, it's really pointless to write those bullet points because it's not a poster that you want somebody to read it later. So try to remove those text. Just put some number as your as a because people, when you speak, people understand it. So use the figures that can cover the entire slides, as opposed to putting a small figure somewhere. So make the figure entirely space completely filled. Each bullet point can be a message. So for instance, you can have 150 slides present in 12 minutes, where each message shows up at one time as a one slide. Animation is not effective. There is no point of putting one figures and just animate one after another on the bullet points. Unless if it is saying something different, then you should have a different picture for it. One thing I would suggest is use Google Slide as opposed to PowerPoint. That way everybody can work on it. So for instance, each person did certain portion of the projects. You can say that you have a 2 or 3 slides. If you want to present that, what you will have those slides, what picture you want to put, what message you want to deliver. So each person can present some portion of it, like 4 or 5 slides. Then you sit together, you'll have lots of slides, right? And then you sit together and then you go through the story making artboard, and then you remove some slides or move it to towards end, and then you finally select a group of slides that tell a story, which is very visual and it's effective, and each slide send one message, not multiple messages. So once you do that one, send it to me. I'll revise the slides. I'll give you some comments or suggestions to change it. That way you are ready for your presentations. So start working on the slides. You don't have to have a complete project to work on the slides, because as you see on the slides, you just need pictures. You are telling a story. So you don't need like a final calculation number. You can just describe what you are doing. Okay. If you have a number, obviously you will present by then. You can continuously update the slides. So start making those stories, start making the slides as a group, as a Google Slides. And once you feel like it's kind of ready, you can obviously share with the TA, and TA will give feedbacks. But before you present, you share with me at least once. That will give you quick feedbacks, what to change, what not. And you are obviously, slides is something optional. I give comments doesn't mean that I enforce it, because you are the one who's presenting. You have to buy into that. So these are my, just take those as the suggestions. Ultimately, I'm looking for a good stories and how you deliver it. So your slide sometimes helpful, but if I say that make the slide certain way and you don't really connect to that, always look for what you think to be done, not what I said. I said in the perspective of audience, what I felt when I listened to your slide or see your slides, but still you have to deliver it. So ultimately, it's your final decision as a team. But projects, I'll give you comments to change. That you have to change, or you should change. So that's all I had for today. Any questions for the presentations or quiz? Anyway, next week, Tuesday, we'll discuss about quiz too. But for wetland or presentation, any questions? If not, then keep schedule a time to meet with me or Renan continuously, so that we can give you feedbacks, so that you finish your draft by week 9. Okay, I'm going to stop recording.